Here's some stuff that's coming up pretty soon. Exam 2 is a week from Wednesday. So what would that be? That would cross the frickin' start of the month, sometime in November. Let's see. What? The 1st, yes. So Wednesday, 11/1 is going to be the second exam. If you can't make it to this class on Wednesday, you can always go to the one on Thursday instead. So it's also Thursday, 11/2, if that's easier for you to get to. The topics for that are going to be everything up through Newton's laws. So we basically, we've covered all the material so far for that exam. Remember that exams are all cumulative, so you need to go back and refresh your memory on the old stuff too, okay? So up through Newton's laws.
Including stuff from first time?
Yes, that's right. Yeah, I do all my tests that way, so the lab tests are that way, the quizzes are that way. I just want you to go back and refresh your memory on everything,
So we get that first test back?
Oh, you don't have it back yet?
Oh, did you?
I don't know. Anybody? I did? Okay. Yes, you can get yours back, and anyone who doesn't have it can get it back. Ask me in lab, and I'll give it to you, okay? But what I haven't given you back yet is lab exam 1, and that is negligence. And but I should be able to get that done by Wednesday, so I'll hopefully give that to you in class on Wednesday. But that's the second thing that's coming up is lab exam 2. It was supposed to be this week, but since I haven't graded the first ones, we're putting it off 2 weeks. So that's going to be the week of so, it's going to be in your lab section the week of, I guess that would be like 11/5 to 11/9 or something like that. And that's just going to be on all of the kinds of questions that I've been asking in labs so far. So, that'll cover everything. Any questions about either of those two things coming up? All right. Anybody have any questions about homework problems or topics or anything? Okay. Well, last time I finished talking about Newton's laws, although we're going to keep using that for the rest of the class, all that kind of stuff. So now we're going to talk about basically Newton's laws in a very specific kind of motion. So our new topic is circular motion. Okay, so there's a lot of different kinds of shapes out there in the world. There's triangles and squares and ellipses and star shapes and everything. Like, why are we singling out circular motion? I mean, you might think like, you can't do them all, like let's just choose one. But really, circular motion is a really important area in engineering and physics. And the main reason is that anytime you have an object moving around a joint, so like, let me, so why circles? Why do we care about circular motion? So imagine a case where you have a thing like this, and this is moving around that joint, like a hinge, okay? Well, every single point on this body is moving in a circle around that joint. That doesn't look like a circle, but it is. Every one of these points moves in a circular path around the hinge. So circular motion just comes up really naturally in a lot of different types of man-made structures, machines, engines. Circular motion just arises really naturally from the motion of rigid bodies. And we'll see that when we start doing problems, most of the problems that I'll give you will be in some way, some kind of rigid body moving around some kind of joint, and then you're trying to figure out the motion of different points because of that. Yeah?
Is circular motion also easier than like other motions, or?
Is it easier? Well, it's not easier than the math is simpler in some ways than like an ellipse or something. You're right about that. Yep, you're right. But really, that's just luck because this is just something that comes up all the time. Elliptical motion does come up in some areas, but not as much. Yeah. Okay, so what's the deal with circular motion? It's mostly based on the stuff we've been doing in lab. So let me say it's largely based on the acceleration exercises we've been doing in labs. So for example, let's think about a circular motion. Let's say this thing is moving around a circular path like that. Let's say it's going this way. And let's say we want to figure out what we can about the acceleration at this point here. Let's say that it's slowing down. So let's say it slows down. As it moves around this circular path. Well, the velocity is tangent to the path in the direction of motion. If it's slowing down, what direction is the parallel part of the acceleration? Opposite this, yep. And I've said a lot of times that to visualize the direction of the perpendicular part of the acceleration, imagine fitting a circle to the path at that point. Well, this is a circle, so it's already fitted, And so it goes toward the center of the circle. That only doesn't look like the center because my circle isn't a perfect circle, but a perpendicular goes toward the center of the circle. Then the total acceleration is the sum of those two. So the total acceleration vector is the sum of these two parts. And so every kind of circular motion problem that we're going to deal with is going to take that kind of thinking. Okay, there's really only three new things that you need to know for circular motion. So there's only 3 new things for circular motion. And 2 of these are just names you have to remember. Okay, the first one of these is for circular motion. We give a parallel its own name. So a parallel is called the tangential acceleration. And I'll always denote that a tan. But just remember that all that is what we've been calling the parallel part of the acceleration. It's just people call it tangential acceleration when it's a circle. Okay, so you don't use that term tangential acceleration for other types of motion, although obviously you could, we just don't, you know. The second thing is for circular motion, a perpendicular is called the centripetal acceleration. And I'll denote that a sin. So again, you're familiar with this idea. It's just it has its own name when you're talking about circles. And this, what does centripetal mean? It means toward the center. Okay, so centripetal means toward the center, and this always points straight toward the center. The tangential acceleration only exists if the motion is changing speed. The centripetal acceleration is there for any circular motion. Well, you know, if something's moving in a circle, it has to be turning. So there has to be a perpendicular part of the acceleration. So this is with every circular motion. And then the last one, this is like the grand finale. This is the only one that's really significant in any way, but this is going to be important. The magnitude of the centripetal acceleration can always be calculated the same way. In the past, we haven't had a way to calculate the centripetal acceleration. But it's always equal to, so there's a couple ways you can talk about the magnitude of a vector. One is to write like an absolute value of a vector that tells you the magnitude, the length of the arrow. Also, a lot of times you just write this without the vector symbol over it, and that's the magnitude of it. But the way you calculate this is the object's speed squared divided by the radius of the circle. So this v is the object's speed. This r is the radius of the circle. And that's really everything in circular motion. That's the end of new stuff. All right, so I'm going to break the world of circular motion up into two things, two categories. One is a very specific category, and the other one is everything else except this one very specific category. So I'll break up circular motion into two categories. The first one is tetherball problems, I'm going to call it. And these are problems where the only thing the object is in contact with is a string or a cable that's swinging it around, okay? So only in contact with a cable. And the circle has to be parallel to the ground. Okay, so you could also take something by a string and swing it around like this, like a Ferris wheel, you know? That's not a tetherball problem. A tetherball problem is only if you're holding it and swinging it around like this. Okay? So the circle is parallel to the ground. And the second category is everything else. So if it's not tetherball, you're going to use this general approach. If it is tetherball, I just happen to have an easier way to do this calculation, okay? Okay, so the first thing I'm going to do today, maybe all we're going to do today, we'll see, is I'm going to give you a general set of steps for solving problems that aren't tetherball problems, okay? So almost every kind of circular motion, this is how you want to approach it. So these are the general steps for non-tetherball problems. Non-tetherball circular motion problems. Okay, the first step is you need to choose a view to look at this problem from. And in tetherball problems, we're going to choose the view differently, but for everything else, you're going to choose a view where the path looks like a circle. Okay, so what that means is if you have something moving around a circular path like this, you know, like that's a toy train moving around on the floor, you could look at it this way. Or you could look at it this way. Okay? If you look at it from the side, you don't see a circle as this thing moves around. If you're looking straight from the side, you just see it go across as it goes around, and then you don't see anything as it goes back to you, and then you see it go across again. Like the path that this guy is looking at, all he sees is this thing going back and forth across a line. Can you picture that? So we wouldn't take this view, okay? This guy, looking from above, sees the circular path. To him, it looks like a circle. And so this is the one we're going to use. I'll use green. Okay, anybody have any questions about that, or you want me to clarify anything? So the first thing is you choose a path where it looks like a circle. Well, in physics and math, the view you take really doesn't matter. What really matters is the coordinate system you choose. And so what this means is that the coordinate system is going to be in that plane that this person sees. Okay, so so this person would see a circular motion like this. The train would be down here. And this person would choose a coordinate system something like this. So when I say view, I also mean that's determining how you're looking at the coordinate system. Okay, second step. Choose a point on the path that you're going to do the calculation for. Sometimes that's given in the problem. A lot of times you just have to choose a point, and you can just choose your favorite spot on the circle. So choose a point along the path to analyze. So in this motion that I've drawn up here, this is our coordinate system. You can choose any point you want. Let's say we're going to choose this point. You definitely are going to want to choose one of these 4 points that are going to make the angles easy for everything we're going to discuss. So you could make things a lot harder on yourself if you chose a point like this in this coordinate system, because you can see like all the angles of all these important vectors are going to be tilted compared to that coordinate system. So don't do that. Okay, so third, draw an arrow from that point toward the center of the circle. Draw an arrow from the point toward the center of the circle. That's the direction of the centripetal acceleration. The magnitude of the centripetal acceleration is the speed squared divided by the radius of the circle. if the speed is changing, so this is one that you might need and you might not need. If the speed is changing, the direction of the tangential acceleration is the same as the direction of the velocity if the thing is speeding up. The opposite direction of the velocity vector if it's slowing down. So that's exactly what you're used to. The magnitude will be given in the problem. You don't ever have to calculate the magnitude of this tangential acceleration. There's a name for circular motion when the speed is changing. This is called non-uniform circular motion. And it makes sense if you just break down those words. Uniform means something's constant, and so the uniform is just referring to the speed. So this would be non-uniform circular motion. What would you guess it's called if the speed is constant? Yeah, very good. So if the speed is not changing, it's called uniform circular motion. Okay? And then the last step, the total acceleration is just the sum of those two parts. Okay? Well, these are the steps that you're always going to do in circular motion problems. I guess I'll give this one and say, at this point, you're almost always going to draw a free body diagram and then use Newton's second law in some way, you know. So I'll say, then a free body diagram, Newton's second law, and so on. At that point, different problems ask for different things, you know. But this is the basic way you're going to approach it. Like if you see a circular motion problem and it's not a tetherball setup, then you can do all this stuff before you even think about what the question's asking you for. You're always going to use this information. Okay? Oh, one thing I want to point out. So notice. Sometimes the view and coordinate system will mean the weight or other forces are out of the plane that you're doing the calculation for. In that case, whatever force is out of the plane just doesn't show up in the calculations, okay? So in that case, leave the force out. So here's an example of that. So think about this train moving on a circular path. We're taking the view from up above. And so This is what we see, okay? Well, now think about drawing a free body diagram of the train, okay? There's a weight force that would be going into the page the way I have it drawn. That's out of the plane we're doing, so you just don't draw that in your free body diagram, and it doesn't appear in Newton's second law. There also, in this case, would be a pushing force from the ground that would be out of the page towards us, okay? Again, that one, since it's entirely out of the page, you just leave that off. All right, any questions about that? So let's just do a couple example problems. So let's say there's a plane moving in a circular path. So, you know, that's the plane. And let's say that this is the radius of the circular path, and let's say that it's 400 meters. And let's say that at this instant, the plane has a speed, well, let's say at this instant. This is where we want to do the calculation at this point P. So when the plane reaches that point P, its speed is 120 meters per second. And it's not changing. So this is uniform circular motion. So first, what's the acceleration vector of the pilot? And second, what's the force vector applied to the pilot by the seat? And this pilot we need to give a mass to. Let's make it 100 kilograms. So what's the force vector applied to a 100 kilogram pilot by the seat? And you can imagine, you know, this is exactly the kind of calculation that people are making when they're figuring out what kind of specifications they need for, like in this case, how strong does this seat need to be? You'd take some of the sort of extreme edge of maneuvers that this plane would be expected to do. You'd calculate these forces, and then you'd say, okay, that seat needs to withstand this amount of force, you know? Okay, so let's just go through the steps. So the first step is we want to choose a view of this motion where we can see the circular shape. So really, that's the view that I've already drawn it from. So for part A, step 1, there's the circular path. Here's the coordinate system I'm going to use. Now step 2, think about where on the path you want to analyze this. Like I said, a lot of times that's totally up to you. In this case, we were told it has to be at this point C, so this is the point that we care about when the pilot's right there, when the plane's right there. Next, draw the centripetal acceleration vector. So that goes from the point that you care about toward the center. So this is the direction of the centripetal acceleration vector. And what's the magnitude of the centripetal acceleration vector? That's the speed squared divided by r. The speed is 120 meters per second. Square that, and then divide by the radius of the circle, which is 400 meters. Could someone calculate that for me? 14,000 what? 14,400. And everything I have is in SI units, so we know this has units of acceleration.
It equals 36.
I got 36.
36,000?
14,400 is 120 squared. Divided
Oh, divide by 400. So what do you get?
36.
Oh, actually, I didn't think of it, but that person would be like a pile of goo if that was the acceleration. Don't ever let yourself accelerate at 14,000 meters per second squared. That's like, 9.81 is 1 g of acceleration. So say 10 is 1 g, So 14,000 is, what's that? Like about a little over 1,000 Gs, So that would be really bad for you. Okay, so 36. That's still pretty high. But people can survive that. Notice that is not the centripetal acceleration vector. That's just the magnitude of the vector. So now we have to take the direction into account. So notice that from our picture, the centripetal acceleration vector is opposite. Well, it's in the negative x direction, right? You see that? It's like the positive x is pointing to the right. It's pointing to the left, so that's negative x. And so the centripetal acceleration vector is negative 36, 0. Okay, well, that's the acceleration vector of the plane, so it's the acceleration of the pilot. They're moving as a rigid structure. Anybody have any questions about that? I didn't use any tangential acceleration because this is uniform circular motion, so it just didn't show up there. Now we want to calculate the force on the pilot by the seat. So let's think about that. So at this instant, when the plane is here, the pilot's looking straight up into the air. So if I draw a free body diagram of the pilot would be sitting something like this. You see that? And if you picture this chair as like a chair you would see in a cockpit, there are two pushing forces going on. There's a pushing force from the seat part. I'll call that R1. And there's a pushing force from the back part on the pilot's back. I'll call that R2. And I always say do the weight first. I skipped it at first, but the weight is 100 kilograms times 9.81, so this is 981. So that's a complete free body diagram. Anybody have any questions about that? So now we can go to Newton's second law. in this coordinate system, the weight force is in the negative y direction, so 0, negative 981. R1 is in the negative x direction, so that's negative R1, 0. R2 is in the positive y direction. So that's all the forces. And this is all equal to the mass, 100 kilograms, times the acceleration, negative 36, 0. And so now we have two equations. We can solve for the two variables. The x equation says 0 minus R1 plus 0 is equal to negative 3,600. So R1 is equal to 3,600 newtons. The y equation says negative 981 plus 0 plus R2 is equal to 100 times 0. Solve that and you get that R2 is equal to 981. Well, if you think of these two things added together as the total force vector applied by the chair, then the force on the pilot by the seat is negative R10, so negative 3,600, 0, plus plug 981 in for R2, so 0, 981. And you get a force vector of negative 3,600, positive 981. Well, that's the force on the pilot by the seat. I guess really if you're doing this as an engineering calculation, what you want to know is the force on the seat by the pilot. What would that be? So what's the force vector on the seat by the pilot now that we know this force? The opposite of this, yep. So this would be 3,600, negative 981. And this is the force that that seat would have to withstand not to break at this instant, you know. Any questions about that? This is all stuff we've done before. It's just now for this specific case of circular motion, we have more information about the acceleration that we can take advantage of because the centripetal acceleration always is equal to the speed squared over r. Okay? Okay, let's say we have a car going around a turn. Ay, that looks terrible. So this car is going around a circular path like this. And let's say that the car has a mass of 100 grams. That's 1/10 of a kilogram. It's a remote control car. And let's say it's going around this way. And the car at the instant we're considering, hold on. Let's say this car is at the instant we care about. The car's speed, that's a capital V, like it's the magnitude of the velocity vector. So let's say its speed is equal to 5 meters per second. It's speeding up at 15 meters per second squared. And the radius of the circle is 1/2 meter. And we want to calculate the net force vector on the car. Okay, well, we're going to go through the same steps as before. So first, we have to choose a view where we can see this as a circular path. So that means from above or below. I'll think of it as a view from above. So I'm going to use this as the coordinate system. And then we have to choose a point to analyze. It doesn't matter in this case which one you choose. The reason it doesn't matter is you could always just imagine that your view at this instant that I've drawn here, just imagine your coordinate system is such that that car is here compared to your coordinate system. You totally can reorient your coordinate system to make that the case, you know? So that's fine. So let's say I'm going to think of it at this point here. The centripetal acceleration is this way. The magnitude of the centripetal acceleration vector is v squared over r. V is 5, r is 0.5. So we have 5 squared over 0.5, and that's 50 meters per second squared. Now we need to come up with that as vector components. The centripetal acceleration that I drew is in the positive y direction. So the centripetal acceleration vector is 0, 50. Okay, is this one uniform circular motion or is the speed changing? Speed's changing, so for this one, we have to figure out what's going on with the tangential acceleration. So what I'm going to do is you know, the motion is this way, right? That's what I drew up above. So let's think about the direction of the velocity, and then we can figure out the direction of the tangential acceleration from that. The velocity vector is tangent to the path in the direction of motion. So there's the velocity vector. It's speeding up, so is the tangential in the same direction as the velocity or opposite? Same. So there's the tangential acceleration. It's in the positive x direction. Do you see that? So the tangential acceleration has a magnitude of this. That's given in the problem. That'll always be given. And it's in the positive x direction. That means the tangential acceleration vector is 15, 0. Any questions about that? So then finally, the total acceleration vector is the tangential plus the centripetal, so 1550. Okay, now we want to calculate the net force on this car to make it speed up like that, to make it go through this motion. So now I'm going to do a free body diagram of the car from the same view that I've been using. And so that's the top of the car. There's a weight force. What direction is the weight force acting? Can you visualize this in this view from above? The weight force always acts down, but in this case, since we're looking from above, the weight force is into the page, and so it doesn't show up in our picture, okay? And it's not going to show up in our calculations. Same thing with the normal force, the pushing force from the ground. The weight is, so the weight is into the page, so we don't draw it. The normal is out of the page, so we don't show it. We don't know the direction of this force, so I'm just going to put in an x component of a force and a y component of the force, and we'll just calculate both of those. So now Newton's second law says this force Fx, Fy, these two components of the force, are equal to the mass of the car, which was 0.1 kilograms, times the acceleration, 1550. This is the net force. And so the two equations tell us that the net force is 1.5 newtons in the positive x direction, 5 newtons in the positive y direction. Any questions about that?
Why did you use the 0.1?
Because I said it was 100 grams. 100 grams is 0.1 kilograms.
Oh. It always has to be 1 gram.
What?
It always has to be
Yeah, if you're doing everything in SI units, you could do the calculations with stuff in other units, but I think it's easier just to put everything in SI units. Okay, let's do one more calculation. So let's say we have one of these astronaut training things, this centrifuge thing. And so there's the astronaut. Going around in a circular path like this. Let's say the astronaut has a mass of 100 kilograms again. What speed would this have to go for the astronaut to experience 5 Gs of acceleration? So what speed, and we're doing this calculation with assuming that it's at a constant speed. So this is uniform circular motion. So what speed would the astronaut need to go for an acceleration of 5g? And let's say that the radius of this circle is 5 meters. Okay, so the first part is we need to pick a view. And this view has to show the whole circle, so I'm going to do the view from above. Choose a point to think about. I guess I'll think about this point here. Here's our coordinate system. The centripetal acceleration is going to be from that point toward the center of the circle. So there's the centripetal acceleration. The magnitude of the centripetal acceleration is the speed squared divided by the radius of the circle. Do we know the speed that he's going? No, we're trying to calculate that, right? So I'm just going to put this in as, for now, I'm going to leave it as v. The centripetal acceleration magnitude is going to be v squared over 5. The way I have it drawn, that's in the positive x direction. So the centripetal acceleration vector is v squared over 5 for the x direction, 0 for the y component. Anybody have any questions about that yet? Okay, well, we want this, in order to get an acceleration of 5 Gs, we want this magnitude to be equal to 5 times 9.81. So I'll write this as 5 times 9.81 is equal to v squared over 5 and then 0. So that says, you know, there's two equations here. The x equation says 49.05 is equal to v squared over 5. Multiply both sides by 5 and you get 245.25 is equal to v squared. Take the square root of both sides. Can someone take the square root of 245.25?
15.66.
15.66 meters per second. This is a speed, so we want the positive, and then that's the answer. So in order to experience an acceleration of 5 Gs on this thing would have to be going just a little over 30 miles an hour. Second, I gave the guy's mass, so let's calculate the force that's applied to the guy by the, well, let's just calculate the net force. Anytime a problem asks for the net force, you can skip the step of drawing a free body diagram and just go straight to Newton's second law, because Newton's second law just says F net is equal to this other stuff. The free body diagram doesn't help, you know. So F net is equal to the mass times the acceleration, which we know now is 49.050. And so the net force would be 4,905 for the x component, 0 for the y component. So that. Anybody have any questions about that? Okay, well, so that's it for today. I'll give you a couple of assignments to do similar to these. You should be able to just kind of, if you set these examples down next to you, you should just kind of be able to follow along until it gets kind of ingrained, you know. We do have lab today. So the lab exam is canceled, but we just have regular lab the next 2 weeks.